In this video, we're going to see the effect of having variable frequency drive VFDs in order to help the motor during its inrush moments and smoothly connect it to the line. To do so, let's create a new project and let's name it VFD test. Let's switch over one line diagram mode and let's create another simple one line diagram, which always includes a power grid, a transformer, a bus, low voltage circuit breaker for the load, and an induction motor and a cable. Okay, now let's make sure that the connections been made. Okay, now let's set the values for each part. The rating for the power grid, we want it to be 12.47 kV, 100% operating voltage. The short circuit would be 99999 as an example, 6% for the impedance, and click on OK. The transformer would step down the 12.47 to 480 volt, and the capacity and kVA rating for this transformer, we're gonna set it to 1500, and the impedance, we're gonna fill it the typical numbers, and for now we're good. And for the load, before setting the breaker and the cable, we're gonna have a 500 horsepower load, because we want to run a dynamic analysis without putting any soft starter or variable frequency drive equipment. And firstly, we're going to connect it directly to the line. We have to select a model. So let's click on circuit, and from eTab library, let's put a sample 500 horsepower P2P. And click on OK. And let's update all the information needed for this motor model, and then go to inertia. Let's set the numbers for each field, the coupling, the load, and the motor itself, like that, and click on OK. I'm sorry, one thing that we missed is the load that is coupled to the motor. We want it to be, as an example, a pump, and this is the characteristic of it. Click on OK, and for the 500 horsepower motor running with 480 volt, circuit breaker needed would be from the library again, circuit breaker that is capable of handling a 500 horsepower load under 480 volts, and it should be for 3-pole load. So let's switch over, for example, Cutler Hammer as a manufacturer, and for this specific example, let's select a 3-pole 480 kV and 600 amp for the trip. As you can see, let's click on OK. So 600 amp. Now let's select a cable for it. So we want the length to be, for example, 100 feet from the library again. We're gonna choose a cable type that can handle this kind of a load. So we want it to be, for example, 3 conductor per core, and I guess 500 MCM would work. Let's put 3 per each phase and OK. Now just to make us sure for the continuity, let's check the continuity of the system. It's OK. Now let's run a simple load flow analysis. Okay, we see the flow of load. Now let's switch over motor acceleration mode and run a dynamic motor start analysis. Oh, but before that, now to run a dynamic motor start analysis, let's create a study case, and for that let's make an event. First event would occur at second 1. In this event, we're gonna have the motor connected to the line, and the whole duration, let's put it, for example, 12 seconds. And now let's click on dynamic motor start analysis. Okay, we can see the motor starts at the first second, and bus 2 and bus 3 are running under marginal state. So let's take a quick look at the graph for the motor terminal and see the voltage. As you can see, the voltage dip is enough to throw the bus into marginal region. We have a significant voltage dip right on the first second. Again, for practicing purpose, let's as a reminder, let's set the axis in order that we can see the first second, and the voltage dip, it's around 90% by double clicking on the horizontal, on the vertical axis, and set the steps to 1, and we can have the major lines, so you can see it's around 90 here. So in order to prevent the bus being around 90% in terms of the voltage dip, we can smoothly, by playing around the frequency and the voltage at the terminal of the motor using VFDs or variable frequency drives, we can somehow help the motor smoothly run during its inrush moment and accelerate until it gets to its full load speed. So now run this, let's make another scenario based on the same one-line diagram, but this time using a VFD. Now let's switch over edit mode, and this time add a variable frequency drive VFD from the toolbar and put it right in between the circuit breaker and the load. Let's double click on the VFD, and first thing we switch to the rating tab, and you can see you have different features of the VFD that you have to decide on, different parameters, but if you only put one of them, it will automatically calculate the other ones too. So in this case, I'm going to put the full load amp of the VFD, which is corresponding to the full load amp of the load connected to it, which is the motor. The 500 horsepower motor, which consumes around 600 amp. So let's put 600 for that and click on somewhere on the window, so all the other fields would be filled. For the horsepower, let's put 500 horsepower, and you will again click on somewhere on the window and you will see the rest would be automatically filled in. Let's switch over, start the device. So we want to use the table on the bottom side of the window, which will define the characteristic of the VFD and how we're gonna bring the motor, the load, up to its full speed as the time passes. So we're gonna create some scheme. The first one is right at the 0 second. It's running at the 0% of its frequency, and 100% of the ratio of voltage per each hertz, and control type is fixed. By adding a new scheme, we will say that at the second we want the VFD bring the speed up to its 40%. And one thing is that, as you see, we are having a 60 hertz VFD and 480 volt nominal voltage. So it's like per each volt, per each hertz of frequency, we are adding around 8 volt. So the ratio here would be 800%, and the control time wouldn't be fixed. It's a ramp. As you can see, we don't want to reach the full speed at one step. It's a ramp. We want to smoothly connect it to the line. And let's add another scheme. In this scheme, we say at 4th second, it reaches the 100% of its full load speed. And again, it's not fixed, it's ramped. And here we go. You can see the curve, the characteristic of the VFD, which is a curve with respect to the frequency and time on its axis. And now we can click on OK and switch over motor start analysis, and once again run the same events that we did for the static. I'm sorry, for the dynamic without any VFDs this time. Okay, now you can see that only at t equal to 1 second, 1.02 seconds, for the duration of 0.94 seconds, the motor is running under voltage because it's an inrush moment. Makes sense. And for the marginal stage, we have the 81% beginning of 1.98 second for 0.1 second duration. If we go and click on motor start, if we go and click on plots and create a plot for bus 2 to see how it looks in terms of the voltage at bus 2, we will see that it's literally, it's a smooth line around 100%, only a little bit of a dip at, again, let's make it more clear. And right in the 5th second, we have a little bit of a dip, but overall it's running around 100% of its nominal voltage. So now you can go ahead and use different type of VFDs, different settings, but this gives you an idea that how VFDs help loads during the inrush and accelerating moments to bring them up to their full load amp or speed.